All right, so continuing from last time, we'll have a little mini review here of the pointers to motivate the the using pointers in a pass by reference scenario. I've got a code visualization tool, the Python tutor here, but for C set up. So let's walk through this line by line. Remember that, of course, from day one, you've been able to create variables normally and just assign them a value. Int a is equal to 10, right? So the way that you create a pointer variable is by using that star syntax, that asterisk, right? And so I've got a ptr a here, pointer to a eventually. Now, what is that pointing to as far as the visualization is concerned here? So what is it currently pointing to as of line 9 or line 10, I should say, right before I set it equal to null? So what is it pointing to? Question mark, right? So it could be dead beef. It could be a random memory location that doesn't belong to you. It could be a random memory location that does belong to your program, but if you end up doing anything with it, you're going to screw up your own memory. If I were to do anything with it right now, it would probably most likely result in a segmentation fault. Right? Just making sure that everything works here. Yep, we're good. All right. So it is best practice to make sure that it points to null or points to something that can actually be checked. So let me go ahead and go to the next step here. All right, now it's pointing to null. Right? If you were to check for this in an if statement, is the pointer to a, is that equal to null? Then you're doing basic error handling, which is what we're going to be talking about here in a moment. Right? Otherwise, I want to make the pointer point to a. That means I'm using the referencing operator, the ampersand. This goes all the way back to scanf. That if you use the ampersand in front of a variable, it gives you the memory address of that variable, so that this pointer can now point to a. There we go. Right, it is literally in the visualization pointing to a here, right? It is a reference, memory reference to wherever a is located, right? Now, through the pointer, you can use the dereferencing operator here to actually set a value. In this case, what this is about to do is it's going to jump to this memory location and fill this in with 20 instead of 10, right? And there we see it done, okay? So again, you've got a regular variable declaration, a pointer variable declaration, you've got the referencing operator, the ampersand, and you've got the dereferencing operator, which is yet another star, okay? Now, how can we use all of this or why would we want to use all of this? Again, I could have gotten away with just simply setting a equal to 20, right? Why do we have to go through all this with pointers and such, right? Well, that's the way that C works, first of all. But what we can do is we can start passing by reference, right? Normally, passing variables by value means you cannot change the values in the original variables. Right? But passing variables by reference using pointers, you can change. I'll emphasize can, change the values in the original variables. Right? For example, that swap demo that we did before, swap, that was only possible with pass by reference, right? Because if you're not passing by reference and you're just passing copies, then yeah, you can go ahead and swap those copies, but it'll have no effect on the original. So now, what other use cases would you have, right? You can now use pass by reference variables to return multiple values. And I'm putting return in double quotes here. I'm not talking about actually returning a value using the return statement. Instead, I'm putting that in double quotes here to say that you can have the effect of returning more than one value. For example, in yesterday's lab, you had, how many sepia functions did you have? You needed to compute it for red, blue, and green, right? That means that you had to have how many functions? 3 things, because you needed to return the red value, the green value, and the blue value, right? RGB. Well, what if you had one function and you passed 3 variables by reference? Now you only need one function because you've got these three buckets that you can fill with the red, the green, and the blue values. That's exactly what you're going to do next week in the same lab, right? It's the same exercise, but instead of writing three functions, three 2-CPF functions, you'll be consolidating those to one function that uses three pass-by-reference variables, right? So computing multiple values, such as red, green, blue, right? Or here's another example as a demonstration, right? Let's compute the tax, tip, and total for a for a diner bill. There we go. I don't know how to spell restaurant, so we're not going to try that. Right? So here's my subtotal, $123.50. Suppose that the tip, suppose that the tax rate is going to be, I don't know, 0.06, in other words, 6%, right? So 6%. All right. Suppose that the tip rate is going to be, how much should we tip? 20% or 15%? 20%? Okay, 20%. We'll be generous, right? We'll be nice. There we go. And so what's the total? Is going to be the tax rate, 6% times $123.50. The tip rate, 20% of that, and add that all together, right? I'll let you pull out your calculators and you tell me, right? Now, if I were to compute each one of these three things, that would be 3 lines of code. Or if I want to put it into a function because I don't want to have to worry about the tax rate, I'll go ahead and put that into a function. I don't want to have to worry about the tip rate, I'll go ahead and put that into a function. Right? I don't want to have to worry about adding it all up, right? And realizing that you don't actually tip on the tax rate and you don't tax on the tip rate, right? All that kind of, those details, I don't want to have to worry about that. I want to call one function. If I did just regular old functions, pass by reference, or pass by value, then that means I've got to have 3 functions to do it, right? We're going to do it with one function in our financial utils class here, right? So let's get rid of that. What I'm going to do is I'm not going to return anything, right? Because I'm going to take 3 values or 3 variables by reference instead, 3 buckets. One of them I'm going to fill up with the tax, one of them I'm going to fill up with a tip, and then the other one I'm going to put the grand total, right? So calculate bill, right? And I do need the actual subtotal. There we go. That is a regular old variable that is passed by value, right? $123.50. I want to now compute the tax, the tip, and the grand total, right? Grand total. There we go. Now, what values would these be? What kind of variables would these be? Definitely not integers, right? Because it's money. We could say doubles, but again, am I going to be able to make any changes to the tax variable that you give me? Nope. So I'm going to make that into a pointer. Likewise, the tip and the grand total are all pointers. Did I spell calculate, bill? Yep, okay. Correctly? There we go. All right, now let's go ahead and actually implement this thing. Again, if I just used pass by value, I would have to have 3 functions because I need to compute 3 values, tax, tip, and grand total. But I'm going to do it all in one function here. Right? So the tax would be what? Tax would be 0.06 times the subtotal, right? Subtotal, that's a regular old variable, so I can multiply it by 0.06. But what about this? Is tax a regular old variable? Nope. So when we've got a regular old variable, we can just use this assignment operator. When I've got a pointer, what do I need to do to set its value? I need to dereference it. So tax will end up being that. Right? Likewise, tip, we said 20% times the subtotal. Right? And now what's going to be the grand total? The grand total dereferenced is going to be the subtotal plus the tax plus the tip. Right? Oops. Tax is not a regular old variable. I can't just add it. What do I do to jump to that memory location to grab its value? Dereference it. Dereference it. Okay? There we go. So now let's come over here to our demo class, and let's call that function. I do need variables to store all those things. Double, tax, tip, and total. All right, there we go. And I will call that function, which was what again? Calculate bill. All right. And I will pass in the subtotal, total, the tax, it was tax tip, is it? Tax tip, and then grand total. There we go. Now this is not going to work. The compiler is going to tell us why this is not going to work. Let me go ahead and compile my financial utilities library first of all. What do I need to pass to GCC to get it to compile a library without actually having to create an a.out file? Hyphen. I just want you to compile, so see. There we go. Uh-oh. All right, so, oh, did I screw something up? I screwed something up. There's also, this is from a demonstration that I did on Friday, I think, or maybe it was Monday. Yeah, this thing here. All right, so let's go ahead and get rid of this for a second. What did I make that into, a void function? Oh, double, all right, double. So that's the first thing, and what else did you say?
There needs to be a comma before tip and grand total.
Oh no, did I have a comma? Oh, in demo class, thank you. I'm not there yet though. There we go. Hopefully that took care of, nope, double result, okay. I've really screwed up the monthly payment thing, so let me go ahead and just get rid of all of this. No, I can't get rid of it all yet. Return 0, 0. Redeclared, result has been redeclared. We'll come back to this because we are actually going to do it. All right, you know what? I don't want to worry about this, so get rid of it all. Get rid of it all for now because I'm not actually using it. There. Go ahead, yeah.
What is the dash C compiled again?
So dash C is for it's for compiling that library, right? There is no main here, right? And there's no main over here, right? So we can't build an executable file a.out. So compile without linking so that it produces this file right here, financialutils.o, an object file. Right? Now I can compile with my demo class, my financialutils.o library, and I can link in the math library because I think I am using the math stuff. Right? All right, now it's telling me that it's not going to work. Why? Let's jump all the way up here, first of all. Grand total is undeclared. Oh, did I call it something else? Oh, total. There we go. There, now ignore that. It starts really right here. Right? Tax is of what type of variable is it? It's just a regular old double variable, right? As declared right here. What's it expecting? A double star, a pointer. So when I pass these three variables in, what do I need to do to turn them into pointers? I need the referencing operator, just like scanf. Ampersand, ampersand, ampersand. Right? Now to verify that this is actually working, let's go ahead and print all this stuff out. So subtotal is equal to percent, or $ if you want to, otherwise %2f. There we go. And the line, subtotal, tax, tip, total. Oh. Subtotal, tax, tax, tip, tip, and total is total. There we go. Total. There we go. Now we're all good because we've got those ampersands in front of it. A.out. So you can pull out your calculators and tell me if it's right or wrong. $123.50. The tax would end up being $7.41. The tip would be $24.70 for a grand total of $155.61. Right. but I did it all in one function. It took care of 3 values in one function. Now imagine next week when you redo your lab from yesterday. Instead of having one function for red, one function for green, one function for blue, you have one function that computes all 3 of those values all at once. Right? So there is a proper use case for using pass by reference. Multiple values computed all at once. Right? Another use case, another useful thing, right? Not returning a value from a function, right? Not returning a value from a function means that you have a void function, right? By doing everything through pass by reference variables, this frees up the return value, right? So not returning a value from a function frees up the return value to be used for other purposes, right? Dot, dot, dot. What would those purposes be? What if I gave it a subtotal over here of, I don't know, negative $123.50? Let's find out. What's this going to report? Negative $123.50. We're paying negative tax. We're paying negative tip. We're paying negative total. Yeah, pretty good, yeah. Unless you got negative food, whatever that means, right? They went into your refrigerator and took your food back, right? All right, so calculate the bill. So what should we be doing before we even do any of this stuff down here? What should we be doing? We should be checking for valid input, right? So if the subtotal is less than 0, then is there any reasonable way to calculate the total of a bill? No. I'm going to return immediately, but I'm not going to return like just with nothing, right? You might, in fact, be tempted to say, all right, well, we should do something here, right? You gave me some bad input. I should inform you of that. And your first instinct might be to print an error message, as you've been doing up to this point. Error, subtotal cannot be negative. All right, there we go. And then you might also be tempted to simply just exit out of the entire program. But now my question to you is this what functions actually do that you're familiar with? For example, if I were to call square root on negative 1, would it quit out of the entire program? No. Would it print anything? No. Right? Instead, it does error handling different. Imagine that if it did. Imagine if it printed something. Well, imagine if it exited first, right? Then that would kill your entire program. That would take the decision-making process away from you, right? We don't want to do that. We want to make a flexible, usable library, meaning that, yeah, we should be informed whether or not there's an error. I want to know that there's an error, but I need to make the decision on how to handle it. Maybe I would if this were read in from the command line, I could give a message back to the command line that said something like, we're not, please enter it again, or something like that, right? But if it just exited without telling me why, right? That's not a good design, right? So we do not want to exit. Right? Now, do we want to print anything? Right? Now realize that software is written mostly for other software. In other words, we write software, why? To automate stuff, right? The stuff that consumers see, right, on their phones or on a desktop or something, that's the tip of the iceberg. The real software doing all the real work behind the scenes, it's never written to interact with actual humans. You don't have somebody sitting there looking at the screen 24/7, waiting for an error message to be printed, and then they jump into action, right? This kind of stuff is important to know. In fact, there are proper logging systems that log to the system with the system logs that tell you something happened at this particular date, at this particular time, and we'll inform somebody if it's a severe error, but otherwise there's a system log. You can go ahead and check it out and try to figure out what happened, right? But we're not sitting there. There's not an actual user sitting there waiting for that to happen, right? So we're not going to do either one of those things. Instead, we are simply going to return. We're not going to print anything. We're not going to exit. But we want to return information that indeed something happened. I'm going to return 1, meaning that I'm going to change this return type from void, because we do actually want to return something. I'm going to change it to an integer, all the way down here to an integer as well. Right? And this is going to be our error code. Return an error code of 1 indicating negative value error. Right, there we go. Anything else could go wrong here? 0, you might consider that an error condition. Maybe it's a different error condition, right? We'll come back to it, right? So does any of this stuff down here get executed if I pass in a negative value? No. So let's come back over here to demo and see how that works. Int error code. I will actually be capturing this error code, and now I can make the decision here, right? Did everything go right? Right? So, or wrong, right? If the error code was equal to, and there was only one error, so it's really easy to remember, right? Printf, you cannot compute a bill on a negative subtotal, right? And here we will exit on them or something, right? Exit 1. Right? Hey, 1, right? An exit code, an error code, right? Oops, end the line, there we go. Otherwise, everything went fine. And so we'll go ahead and print this out. There we go. Except that, how do I know that everything went fine? If it's not an error code of 0, I have to return something down here. Right. So, 2? No. Negative 1? No. Think back to Boolean values in C. What was false again? 0. What was true? Anything else? 1, 2, 3, 4. So now follow that same pattern here and ask yourself, was there an error? False. No, there was not an error. 0. True. Yes, there was an error. We're going to return 1. Maybe there was a different type of error. Else if something. We'll come back to it. I can return a 2 to indicate a different type of error. Right? I could return a 3 to indicate yet another type of error. I could return a 4 to indicate yet a different error. Right? We're not there yet, so I'll go ahead and get rid of that. But 0 is no error. 0 indicates no error. Okay? Now let's go ahead and compile everything again. Compile that, compile everything together, and run it. There we go. You cannot compute a bill on a negative subtotal. Much better than getting this nonsense output here. Right? But we're handling it through error handling. That one function is able to communicate back to another function. There is something wrong, right? You handle it. It's your choice about how to handle it. I'm not going to. I'm not going to quit on you. I'm not going to print anything. That's for you to decide what to do. Okay? Can anything else go wrong here? So, remember what Bret Hart said. Bret Hart said, careful, you are dereferencing a null pointer. Right? What if I gave it a null pointer here? Let's walk through that. So, tax is null. Right? Subtotal, that's fine. That's now $123.50. That's good. But I come down here, and tax is now null, meaning that I am trying to dereference a null pointer. What's going to happen? Let's find out over here. Let's edit this. Try to dereference a null pointer. Instead of pointing it to A, let me get rid of this. We never actually point it to A. Instead, we're pointing it to null, and then we try to change its value to 20. The compiler's not going to catch that. I doubt that there would even be a warning. Oh wow, okay, that is catching it. All right, fine. Over here, it won't catch it. Let me change this to tip. There we go. And let's go ahead and run this again. There. That looks familiar. Right? Remember, if you forgot a ampersand on scanf, it would be a segmentation fault. What does that mean again? There is a segment of memory that you have faulted on, that it doesn't belong to you, right? It doesn't, or maybe it doesn't exist. You've tried to access it and set its value equal to 0.06 times $123.50, right? You can't do that. You are dereferencing a null pointer, smack, right? So we should check for that. Else, if the tax given to us was null, then I'll return a different error code. Return an error code of 2 indicating a null pointer error. Right? You gave me something bad. Right? What else could go wrong? Well, if I've got one pointer variable that could be null, what's to stop me from making this one null? What's to stop me from making this one null? Let's check all of those. If tax is null, all right, here, and tip is null, is that the correct logic? Nope. What should it be? Or. If that one is null, or if that one is null, or if that one is null, all of those are going to be errors. Grand total is null. There we go. Okay? So if any of those happen to be null, then the show is over. We can't do anything with them. Otherwise, we would be, oops, tip, tax. There we go. Oh, this is tip. This is tax. All right, there we go. Tax tip. There we go. All right. Otherwise, we would be dereferencing null pointers all over the place. Okay. Another style tip here. This kind of looks like multiplication, like add and then multiply. If you want to, you can go ahead and surround. In fact, sometimes it's necessary to surround things with parentheses. Now it's absolutely clear that that thing is going to be a dereferencing operator. Right? The dereferencing operator has actually a higher order of precedence than multiplication, so the compiler is able to understand this as dereferencing. Right? If you want to, go ahead and surround them with parentheses to remind yourself that those are dereferencing. Now here's another question. Else if, what was the what did I call the first one? Subtotal? Subtotal. If that is that null? Do I have to check for that at all? Pointers are null. Are regular old variables ever null? No, because they're not pointers. They're not memory addresses. It's a number. It's like 42 or 123.50, right? So this is not something that you have to check. You only check for nullity or null pointers with pointers, not regular old variables. So let's take care of that over here now. Right? Else if error code is equal to 2, I think, then we'll go ahead and print an error message. Something went wrong with memory. Something went wrong with memory. Right? Now here's a good parallel to real life, right? If you just have a regular old user, right, that doesn't know anything about programming, doesn't know anything about computers at all other than how to use them, should I print out a blue screen of death kind of message? In other words, here, I think we can look up what it looks like. Blue screen of death. Right? Anybody who's used Windows for a long enough time will have seen this at one point in their life, right? Something like this, right? And then if you actually look at the details, or if you look at a report, it'll have all this memory dump, a bunch of hex numbers, what happened, where. Like, is a regular old end user going to be debugging that stuff at all? No. So what if I gave them a message like a null pointer occurred, right, at memory address 0x whatever, right? Is that a good error message? That's a good error message for somebody who knows what they're doing and is responsible for the system and is responsible for debugging the system. But is that a good end user error message to a regular old user? No. This is a perfectly good message for a regular end user. Right? The blue screen of death is not. I could just say something went wrong with memory. Contact Joe or Jane or whoever's in charge of it. Right? There we go. All right, that's good. Right? I can even exit with a different error code, 2. There we go. So let's go ahead and try this again. And all of it, I need to do that one and then this one. There we go. and I'm going to get something went wrong with memory. Okay. Restore this to tax tip, and let's make sure that we're regression testing here, and everything still works with $123.50. Great. Now, come back even a week from now, certainly a month from now, years from now. Are you going to remember what an error code of 1 meant? No. I mean, you can tell that just by reading this right here, but you shouldn't have to read the context. Your code should be self-documenting. Right? Are you going to remember what error code 2 meant? Nope. You need to add a new error code because you found out that there isn't a user that entered a certain input and it caused a different kind of error. So what was taken already? 1 and 2. Was 3 taken or not? I'm going to have to dive into the code to find out. Right? So there must be a better way of doing this. Do you remember what we called these things? What is 2? What is 1? What is 0? Right? Those are magic numbers. Right? We don't like magic numbers because where did they come from? What do they stand for? Right? What I want instead is a human readable message. Right? And you already know how to do this. Let me come up here and define them. Right? Define. What were the kinds of errors that we were looking for? Negative input error. Right? That was 1. Define null pointer error. That was 2. Right? Define no error. That was 1. Or that was 0, excuse me. Right? And now I've got human readable counterparts that I can use instead of 0, 1, 2, etc. Right? And do I have to worry about what was taken before? Well, I'm going to have to create it again, but we'll take care of that here in a second. So negative input error, I can use that down over here instead of returning 1. There we go. Negative input error. Not only that, but what can I do with this crufty kind of documentation now? I needed this documentation because I needed to remember that 1 stood for negative input error. Do I need that anymore? No, because it's in the code. Right? It's self-documenting now. Right? We're still seeing a lot of folks putting this stuff in, this cruft stuff in. Take it out. Leave it out. All right. What about 2? 2 was null pointer error. Now I can return that. What about this? Indicates no error. Well, the words no error indicate that. Yeah, no error. Okay, great. Now over here, I don't have to have any guesswork. This was a null pointer error. This was a negative input error. Right? And this was no error. Right? And it all still works, but now it is much more maintainable because it is much more readable. Right? It didn't change anything. Right? Except that our code is now way better, right? Design-wise. That's one way that you can do it. Here's an alternative, and so here's some new syntax for us. Right? I'll keep it down there because I'll cut and paste from it. I want to define my own type. Now, what is a type? We've been using types this entire time. An integer is a type of variable. A double is a type of variable, and a character is a type of variable. And some of you have been using floats. Again, we recommend against it because it's just a less accurate double. There are use cases for floats, but just keep everything consistent and just use doubles. Right? All right. So those are the types. You can define your own type. Type def. That's short for type definition. The type that I'm going to define is an enumerated type, or enum for short. Okay. What is an enumeration? Like a bullet pointed list or just a list, right? Item number 1, item number 2, item number 3, item number 4. An enumeration is nothing more than a list. That looks like a list to me, right? So let's go ahead and put this stuff up here in my enumeration. Oops, come on. I'll start with 0, then comma, 1, comma, and then no pointer error, comma. There we go. We're not done yet. One observation that I would make here is this comma necessary? Now, I don't know if other people call it this, but I call it the coding Oxford comma. What is the Oxford comma? I want cake, ice cream, comma, and cookies. There we go. Right. What's the Oxford comma there? That little guy right there. It is optional in the modern way of writing, right? Why is it the Oxford comma? I don't know, right? That's just what it's called, right? This is the coding Oxford comma. Because it's the last one in the list, it's not necessary. But you'll find that a lot of people still include it. Why? Because what if they come back and they find a brand new error code that they want to match the keyboard on? Comma. Another one that they want to match the keyboard on. Comma. Right? They don't have to remember, oh, I forgot the comma, and then go back to it. Right? It's just a style thing. Okay? Now, we're not done yet because this is a declaration. So we do need a semicolon, but we need to give it a name first. An integer's name is int. A floating point number's name is double, double, right? A character's name is char. What should we call this thing? Well, what is it? Remember, there are only two difficult things in computer science. One is cache invalidation, the other is naming things, right? So this is the most difficult thing that we'll be doing today. Just call it what it is. What is it? Types of errors? Well, type is already up here. It's an error. You could just go error type, or error code is what I was calling them before. I'll go with that. Okay? Now, the advantage of this is that you can now change the return type here. It's no longer an integer. It returns an error code. Right? Over here in .c, it returns an error code. And over here, we don't have to call this an error code anymore, an integer. It's just an error code. We've defined our own types, and we'll do this again later when we want to define, well, what is a student? A student is a first name, a last name, an NUID, a GPA, a whole bunch of things, right? I want to collect that all into one type called a student type. Because not everything in the world is just an integer or a double or a character. We have complex types that we want to define in our code so that we have data organization like this. This is our first type. Right? Now you can do error handling either through the define preprocessor macros or this way. And which one is best? Half a dozen of one, 6 of another. Right? There are advantages to one and disadvantages to it, and then there are just different advantages and disadvantages to the other one. All right, so there's our error code. And let's make sure that it compiles. There we go. There we go. And again, nothing changes, but our code is more maintainable and more readable. We'll discuss this in more detail as we formally cover error handling, probably starting Friday. Right? What else could we do with a remainder of 5-10 minutes here? Right? What about round descents? We could check for error handling there. Right? What about now? Let's restore this. What about get monthly payment? Let's go ahead and change that to return an error code. Right? It takes a principal, an annual percentage rate, and a number of years. But now it has a result that is returned. And again, it's not returning anything. It is returned through a pass by reference variable. I don't know, monthly payment. Right. That's why we called the function get monthly payment, because functions are verbs, variables are nouns. Right. Let's change this now, and I think we started changing this the last time, but let's go ahead and do it fully now. There we go. All right, what are some error conditions here? The principal could be 0 or negative. So if the principal is less than or equal to 0, then I will return an error code of 1. Later on, I'll make sure that I'm taking away those magic numbers. Else if the annual percentage rate is less than 0 or the annual percentage rate is greater than 1, right, then I'll return a different error code, 2, invalid annual percentage rate. Else if the number of years, oops, is less than or equal to 0, then you're not actually taking out a loan. Return a different error code, 3. Right? Else, and then you don't need an else here because you've either returned at that point, so you can go ahead and put the rest of this in one big chunk. There we go. So the monthly rate is going to be that thing. The number of months is that thing. Temp, I'll call that temp. We round it, and then the result, I didn't call it result, what did I call it? Monthly payment. There we go. Is equal to that thing. Now, 0 by convention is no error, so what do I need to return at the end if everything else went great? 0. Now I can get rid of this cruft. Question though, let me give myself some more room here. I've been writing it correctly the entire time because I wanted to show you what it looked like to be correct first. One common mistake we see is something like this. Okay? Now what's wrong with that? You're making all these calculations based on the assumption that they're all correct, right? Then you're checking for them after you've done all your calculations. Right? Oh, by the way, we also need what? Else if monthly payment is null, then we'll return a different error code, 4. There we go. Right? What would happen here if I had the code like this? Right? If you're about to enter a dangerous situation, do you leap before you look, or do you look before you leap? Right? You're about to walk off of a cliff here, right? Do you look before you take another step, or do you just go ahead and take another step and then look on your way down? Which one do? You look before you leap. We are doing error handling, checking, before we do this potentially dangerous stuff. This could be a dereferencing of a null pointer. This could be nonsense, right? If num months, or if num years is -5, then num months is going to be -60, right? You're going to get something out of this, but nothing meaningful, right? We're going to look before we leap, and we're going to immediately return without leaping. It's like walking up to a precipice, a cliff, and look. Okay, that's dangerous. I'm not going to take another step. I'm going to go back to where I came from. I'm going to turn around and go back, right? I don't jump and then check. Oh, I shouldn't have done that, right? And then I turn back because at that point there's no turning back. You have dereferenced a null pointer. You have computed some nonsense, etc. Right? So error handling is always the first thing you do in a function period. You do not exit. You do not print anything. Instead, you return an error code. All right? Any questions? No? All right. I wonder what would this do then? It's not even going to let me do this. How do I obfuscate that? How do I force it to do this? I can't force a seg fault? I know what to do. I'll confuse the compiler here by setting it properly and then setting it back. I bet it won't catch this now. Oh no, it is. Darn it. All right, fine. I'm not able to set it's way too smart here. Right? Our compiler over here isn't smart enough to see that. But anyway. We will be looking at additional tools that basically what this is using behind the scene is probably some static analysis tools. We'll be looking at those static analysis tools later on. Right? But otherwise, we'll continue there on Thursday. We should have, remember that Lab 5 was extended to an hour and a half from now. And we'll have exam 1 graded by tomorrow.